Hi, welcome back. So we are in Chapter 6, Prediction by RCC, the outline prediction by clustering. Last part of this map where we have introduced previously this side of the map. Now we are on the side when the data is unlabeled. In other words, we do not have a specific feature that we would like to predict. This is the case when we call unsupervised learning or unlabeled data. So if I would have just only for simplicity for now, I bring in a two-dimension, easy to graph in one, and then these n number of data set, and the graphic representation of this might be in two-dimension, looks like so. The point of clustering in general, it tries to go throughout this data set and see how these points have clustered. And here where is one of the most popular kind of algorithm, so to speak. It's rather not actually a framework in particular, but it's like a few steps that if you follow, perhaps it can lead you to a new idea of clustering, and that is called the k-means clustering algorithm. And the k-means basic idea, it relies on the concept of predefined this number of k, represent the meaning of number of clusters. Well, when we had the supervised learning or a labeled data set, that there were labels. Maybe you can think of cluster as sort of label. How many clusters are there? It should be for this data set. That's why it's a very controversial. There are many techniques, of course, that they are trying to optimize this k, trying to see what's the best number k can fit. If I assume that there are two clusters. Now, the question is, what do we mean with these clusters? Again, think of them. These are the labels, actually. We are creating here a completely new column that is telling you, well, this point is belong to C1, this point is belong to C2, C1, and so on and so forth. We would like to pick this here, completely random. These are the centroid of my cluster. And this is where we want to translate them in the form of x1 and x2. So another word to say, well, my first centroid is going to be x1 and x2. And for the second centroid, again, it's going to be x1 and x2. Now we have two centroids. I want to find a distance between this point and the centroid that you are talking about. Imagine here if I take point 1 and I want to find its distance from C1 and its distance from C2. There are many different ways of measuring the distance. I will leave this for you. So let's just rely on the simplest case that we know this distance, the Euclidean distance. And the same thing I could do for the second point and go all the way to n number of these guys. You can see C1 and C2. What we want the shortest distance, and to do that, well, I could look at both values of C1 and C2, the distances, and I will choose the minimum. Same, so the minimum distance will be picked up here, and so on and so forth. We did this one time. Completely random, we picked up C1 and C2. Now we have C1, the first centroid, and the second centroid. And after we did the first work, some of these points will lay down here. So, for example, the first point, the 7th point, and here other point, maybe the 5th one, maybe the 11th one, whatsoever. Let's go inside here, sum up all these points and find the mean average of them. In other words, to say, well, I know each point has a value of x1 and x2. Isn't that true? Well, let's sum up all these points. Let's sum up all these points and get their average here. Now, I have a new C1 represented only with a single value of x1 and x2. And same thing if I did do the average here, I would have now x1 and x2. Great. Now I have completely new values of C1 and C2. Well, now I have C1 and C2. Why don't we go and play the game one more time and keep doing this again and again and again? But the question is that, when are we going to stop? Let's say condition of stop. The first one based on number of iteration, like say we decided to do this 100 times. So it's obviously after 100 times I'm over and it's fine. But if you think about it, there is a converge gonna happen. Maybe after 100, maybe even need 1,000 to happen. You see, in the first time we did this, maybe there can be some changes here. In the second round, again, there's some changes again. I mean, in terms of the distance, I'm saying. If we construct a condition to say, well, if we store the differences of every previous session. So for example, previously we have a set of points decided for C1 and C2. Now when we start the new iteration and we see what's the outcome of this, let's go ahead and check, is it equivalent to the previous distance that we know? It means, are there any changes that happen? If yes, continue until the iteration is over. If no, that means there will be no changes anymore. So every point have been dedicated to a certain centroid or cluster. And this is where we can make the second stop condition, so to speak. That's the entire idea of k-mean cluster actually in general. Now let's go to Python actually and implement the very basic idea of this algorithm. Let's create just a 20 points of random here. So what we've got here, we got these points and would like to create a cluster and find patterns, cluster them. So here's function. Everything I've been talking about is just in these few lines. So if you run this, there were a few steps when the conversion happens. So if you trace this back, and to see them actually they are quite clear by just graphing. You could change to 2 clusters whatsoever. Anyway, that was all actually what we needed to know about this side of the map. Last thing maybe we gonna add on feature extractions. Let's go ahead and close down the last bit of this material. I will see you then.